All right, everybody, very good to see everyone here this afternoon. How's everybody doing today? Doing all right? Thumbs up, good, okay, very good. So how did everybody get on last week with kinematics? What did everybody reckon to that? How are people feeling about the kinematics? All right? All right, okay, fair enough. Did anybody give the challenge question a go in the workshop last week? Did anyone give that a go? So if you didn't give it a go in the last workshop, it's still quite a helpful one, especially if you're still kind of getting to grips with kinematics. So maybe we might give the challenge question another go in the workshop coming up on Friday. Now, the subject for today, we're going to be focusing on Newton's laws of motion. Now, has anybody done Newton's laws of motion before? Around? Oh, okay, so some people, what is that, about a quarter? Okay, where have people done Newton's laws of motion before? Where have people done in previous physics courses? Physics, okay. Where do you, A-level physics? Okay. Has anyone done Newton's laws of motion somewhere other than A-level physics, or was that the main place people have done it? Okay, so if you have done Newton's laws of motion before, hopefully there's going to be some interesting new angles on it here. And then, of course, if you haven't done Newton's laws of motion before, that's absolutely fine as well, because we're really going to be taking a fresh look on it, okay? So let's take a look at what the plan for today is, okay? So we're really going to be thinking about Newton's laws of motion all week, actually. That's the kind of theme for the week, okay? And we're going to be starting today just by thinking, well, what are Newton's laws of motion? Now, you may have heard maybe there's the three laws of motion, very important in physics, because they really describe the motion of everything there. Very important universal laws. So we're going to start just by figuring out, well, what are Newton's laws of motion? Something I'd really like to emphasize today is that when people are learning Newton's laws of motion, there's lots of misconceptions. It's very easy to get things a bit the wrong way around when it comes to Newton's laws of motion and end up with some misconceptions. So just a warning, if you are reading up about Newton's laws of motion, maybe online, on forums, things that people have posted, just a warning, there are very often lots of misconceptions with Newton's laws of motion when it comes to that kind of stuff, okay? Sometimes we even see that there are misconceptions being taught when people do Newton's laws of motion in school. So hopefully today we can kind of take a fresh go at this and get things right off the bat, okay? And clear up any misconceptions that people might have about Newton's laws of motion. Once we've got a feel for what the laws are, hopefully cleared up any misconceptions, our main focus is going to be looking at applications and examples of Newton's laws of motion, because it really helps to see how these laws apply to understand what is going on. And one of the classic examples that we're mainly going to be focusing on next time is this situation of terminal velocity, which is this very exciting sounding thing that you get when you go skydiving. Now you may say, well, I don't really like the sound of going skydiving, that's not for me. Do I really need to learn about terminal velocity? And the answer is that it's a really important situation to understand if we're trying to figure out what's going on with Newton's laws of motion. So we're going to be focusing more on that on Thursday. Now, before we dive straight in to seeing what Newton's laws of motion are, I'd like to take just a few moments to think about the photo that I've got to kind of connect to what we're thinking about for this week. Has anybody seen this picture before? Has anyone seen this one before? Okay, a few people, but not too many people actually. So for me, this is the most important photo ever taken, because it really is a photo of everything on Earth. So as you can read there, this photo was taken by Bill Anders, who was one of the members of the crew of Apollo 8. Does anybody know why the Apollo 8 mission was so important? Does anybody know why? So Apollo 8 was the first space mission to ever leave low Earth orbit. It was the first ever human mission to take humans beyond low Earth orbit and to fly around the moon. They didn't land on the moon, but they were the first humans to ever leave Earth orbit and go around it. And as they were emerging around from the other side of the moon, that was the very first moment that humans had ever seen with their own eyes planet Earth rising over another celestial body. Now, humans had already seen planet Earth from orbit before, but this moment was the first time that humans had ever seen planet Earth really as another planet up there in space. And there's a couple of very important points about this when we're thinking about learning Newton's laws of motion. Now, first of all, if you want to send a spacecraft and go and fly it around the moon, obviously you have to have a very solid understanding of Newton's laws of motion. I certainly wouldn't want to go in a spaceship around the moon that was designed by someone that didn't have a very good idea of what was going on. So there's a very direct connection to what we're going to be learning about. The other slightly more subtle connection that we're really going to be thinking about today is very often when we're learning physics, it's easy to think, okay, well, maybe we're in a lecture theatre, or we're in a university campus, or we're in a city. And it's easy to forget that we in fact live in a planet in space. Now, of course, we're all aware of the fact that planet Earth is a planet in space. But I think seeing a photo like this really brings it home, and it really emphasizes the point. And a lot of the misconceptions that people have when we're studying Newton's laws of motion, they come from forgetting this fact. They come from forgetting the fact that planet Earth really is a spaceship out there in space. It's not just a university campus and space that's something that's out there. Space is the real deal, and we're something which is in space. And really, by appreciating that, that actually really helps us to understand what's going on with Newton's laws of motion. So let's just bear that in mind when we get to see what some of the laws are. For me, it's really that appreciation, not just the knowledge of the fact, but the appreciation that planet Earth really is this celestial object in space, which is one of the most important reasons for studying physics and astrophysics, because it really does change your perspective on everything if you really appreciate this fact. And that's really what I like so much about this photo, that it's the first time humans ever saw that with their own eyes. And that's why I think it's so important. That's all I wanted to say about Apollo 8 and the moon and that kind of stuff for now. So I think let's get straight into business and start by thinking, well, what are all of these Newton's laws of motion? Now, you might have heard that there are 3 of them, so I think let's start with the first law. I think that is a natural place to start. So let's start by having a think about what is Newton's first law of motion. Now, I have a question here for you guys, thinking about which one of these laws is Newton's first law of motion. I've made it a bit interesting for you guys by taking several other well-known first laws, and I have somewhat mangled them with a bit of artistic license to sound a bit like Newton's first law of motion. So my challenge for you guys is, can you figure out which one of these 4 mangled first laws is the genuine Newton's first law of motion? Maybe you can recognize what some of the other first laws of motion are, and that might help to narrow it down a bit. Okay, let's take a look at the responses. Let's see what everybody thinks. Which of these is the genuine Newton's first law of motion? Let's have a look. Okay, looks like people are mainly going for option B there. Okay, so very well done, everybody who gave that one a go. That's the correct Newton's first law of motion, option B there. Can anybody recognize where option A is? Which first law is option A? Does that, yes? I think you're thinking on the right lines. You're thinking on the right lines. Very good, very good. Kepler's first law of planetary motion. That's excellent. Very good, very well done. So that is actually, I somewhat mangled Kepler's first law of planetary motion. So Kepler, he also had 3 laws, but they were about planetary motion, and they actually influenced a great deal Isaac Newton when he was developing universal laws of motion. So that's the first one there. So well done for spotting that one. What about option C? Can anybody recognize which first law is option C? Yes?
Law of energy.
Yeah, excellent. Very good. Very good. So did everybody hear that? So option C, it's the law of conservation of energy, otherwise known as the first law of thermodynamics. Now, in just a couple of weeks, we're going to be learning a lot more about energy and heat. So just remember, I've slightly mangled that one. Maybe we'll recognize that one when we see it really written out properly as the law of conservation of energy. Now, what about the last one, option D? Can anybody spot what's the first law there? Yes. Yes, very good, very good. So option D, it's Asimov's first law of robotics. So I've just taken a bit of artistic license to kind of make it look like it's maybe a law of motion there. And obviously, unfortunately, motion may in fact end up injuring a body there. So you might have been able to narrow it down and figure out that wasn't genuinely Newton's first law of motion. So very well done, everybody who gave that one a go. It looks like people kind of got that one right. Okay, so that's a great start. Now, that's what the law is. And if we were just doing Newton's first law of motion, you might say, well, can we just wrap the lecture up at this point? Okay, but clearly there's more to understand, because as well as just knowing, well, what is Newton's law of motion, we really have to understand what it means for the kind of dynamics that we've been learning about for the past couple of weeks. So let's try another question and see how Newton's law of motion relates and affects things when we have a kind of dynamic situation like we've been learning about. So let's try this question over here. So what does Newton's first law of motion tell us if our velocity is constant? And I'll just give you a clue that all of these could potentially be true. But what Newton's first law of motion tells us, it's the most general version of these. All right, let's take a look. Let's see what Newton's first law of motion is actually telling us about motion. Let's have a look at your responses here. What's everybody think? Okay, going for option A mainly. No one's going for option D. So very well done, everyone who gave this one a go, because it is a bit trickier. Because if our velocity is constant, then maybe actually all 4 of these options could be true. So if our velocity is just 0, well, 0 is constant. So that is actually true. Maybe the force of friction 0. So if something's sliding on an ice rink, force of friction is 0 and it's just sliding with constant velocity. Or maybe there's no forces acting on objects. Maybe it's just out in space. There's no forces acting on it, and it's just moving along with a constant velocity. So all 3 of those could be true. But I think, as most people have got, the most general option is option A here, that the resultant force has to be 0. That's the correct option. So very well done, everybody who got that one. That's kind of really starting to think a bit more like a physicist there. That's the reason why, when we were doing vectors, we spent a lot of time thinking about the resultant of forces, and we did spend quite a lot of time calculating the resultant of forces, because it's the resultant force, whatever all the individual forces acting on it, that really affect the motion of an object. So that's why it's so important. Now, that's Newton's first law of motion, and I think for the time being, let's leave it at that, and let's move on to the next laws of motion, okay? So let's move on to Newton's second law of motion, see what everybody thinks for that one. So Newton's second law of motion really gets into telling us, well, what actually is a force? And it tells us that force, it's the product of mass and something else. So let's see what you guys reckon for the something else. Okay, very good to see all those responses coming in quickly there. Let's see, well, what does Newton's second law tell us about what a force actually is? Let's see. Oh, okay, well there it is, it's coming. It's D. It looks like most people went for D anyway. So, yeah, and that's really what Newton's second law of motion tells us. It tells us that force is the product of mass times acceleration. Now, we've actually been talking about forces quite a bit over the past couple of weeks, but this is really the first time that we've ever actually written out definitively, well, what is a force? And now we can say from Newton's second law of motion, force, it's mass times acceleration. So in other words, if we have some mass and we want to accelerate the mass, what we're going to need is a force. That's what Newton's second law of motion tells us. So very well done, everybody who got that one. And it gave the game away a bit there. So you guys all know that you got that, okay? Now, we have already covered what the units of force are. But you guys probably know by now how much I like units. So what I'd like to do, now that we actually know what a force is, let's think about what are the units of force in terms of those SI base units. So I've got this question here, and we're thinking, well, what is 1 Newton of force in terms of the SI base unit? So let's give this one a go. I'll move the code out the way so you don't just have to take a chance on mystery option D. Let's see what everybody gets for this question. Now, with this question, you don't have to guess if you're not sure. Because remember, we know what a force is. It's mass times acceleration. So based on what goes into this, we know what has to come out. So think about, well, what are the units of mass and acceleration? That's going to have to give us the units of force. Let's take a look at the responses here. Let's see what everybody thinks for what is 1 Newton in terms of the base units. Okay, most people seem to be going for B. Now remember, like I said, you don't need to guess with this one. Okay, so we know that the mass, that's going to give us the kilograms. So we really just have to think, what are the units of acceleration? Now remember, acceleration, it's the rate of change of velocity, and those units are meters per second squared. So when we put them together, we get the correct unit there, option B there. So very well done, everybody, with that question. Okay, so 1 Newton in terms of the base units, it's 1 kilogram meter per second squared. So very well done, everybody who got that one. Now, you might have seen Newton's second law of motion before written down as F equals ma. But there's actually a very important equivalent way of writing down Newton's second law of motion. So what I'd like to think about in this question is how else can we equivalently write down what Newton's second law of motion is? Which one of these statements is equivalent to F equals ma? So it's a bit trickier. So have a think about which of these concepts it could be. Have a think about the units. Have a chat with the people around you. Let's see what we get for this question. Okay, let's take a look at the responses. This is a bit of a trickier question now. Let's see what's an equivalent way of writing Newton's second law of motion. Let's see what everybody thinks. Okay, all right. 80% people going for rate of change of momentum, option A there. So, very well done, everybody who gave this question a go. Let's just take a look at what's going on here. So, remember, so we've got that force is equal to mass times acceleration. That's what we saw originally for Newton's second law of motion. Now, generally, we're not changing the mass of something if we're applying a force. Generally, the mass is probably just going to be keeping constant. So suppose we're thinking, well, if the mass is constant, let's see what the momentum of something is. Remember, momentum, P is equal to mass times velocity. So if we keep the mass constant, then the rate of change of this is just going to be mass times the rate of change of the velocity. And remember, the rate of change of velocity is acceleration. So we have ma, which is equal to force. So the rate of change of momentum is an equivalent way to defining a force, which is what we got for option A. So very well done, all of you guys. That is really good work. That's really impressive. Rate of change of momentum. Does anyone have any questions, anything they want to ask at this point? Now, if you don't have anything you want to ask for the time being, I will just reiterate my challenge to everyone to try and write down one question from every lecture that you go to. Now, you don't have to ask it during the lecture. Maybe we can have a chat about it in the workshop, but really do try and just write down one question from every lecture, because it really helps to think about everything that we're going over, okay? Now, very well done, everybody who gave this question a go. I think if there's no questions for the time being, let's move on to the third and final of Newton's laws of motion. Let's see what we think for Newton's third law of motion. So Newton's third law of motion tells us something about forces. Now again, I've spiced this question up a bit for you guys because all of these options are true facts about forces. A force does have all four of those things there, but only one of them is the thing about forces that Newton's third law of motion tells us. So maybe have a chat with the people around you. Maybe you can eliminate some of the other options. See what you think. What does Newton's third law of motion tell us about forces? Okay, let's take a look at the responses. What does Newton's third law tell us about forces? Oh, okay, so most people going for D. Okay, now very well done if you gave this question a go, because these are all true things about forces. So one of the first things we saw, remember forces, they have a magnitude and direction because they're vectors, but that's not what Newton's third law of motion tells us. Now, force is equal to mass times acceleration, and as we just saw, that's also equal to the rate of change of momentum. But you could probably eliminate that because, of course, that's Newton's second law of motion. So, well, we're left with option D. Every force has an equal and opposite reaction force. So that's the correct option. So very well done, everybody who got that one. Now, of all three Newton's laws of motion, I think it's option 3, the third law, that has the most misconceptions. It might seem quite straightforward to write down and you say, okay, reaction force, every force has got a reaction force, doesn't seem too complicated. But in practice, there's a lot of misconceptions with it. So let's try another question, thinking a bit more about the force, about what we get when we have a reaction force. So you might hear when people are talking about Newton's third law of motion, they might say it as every force has an action-reaction pair. And that's true, but what can we say in detail about what must be going on with that action-reaction pair? Let's give this question a go. Let's see what we reckon to this one. Now, unlike the previous question, only one of these is a true fact. The other ones are just hopefully somewhat plausible sounding nonsense. So see if you can spot which of these is the true fact about Newton's third law of motion. Okay, let's take a look at the responses. Let's see what everybody thinks for this one. Okay, so a bit more evenly split there. This is a bit of a trickier question. So well done if you gave this one a go. What do we have? A, B, C, D. So most people going for option D. Now, just to explain what's going on there with this basis vector components and the opposite and the same kind. So do you remember when we were doing vectors, and we could either write a vector as, it has a magnitude and then some direction, so it's pointing in a certain direction, or we could write the vector in terms of components, so like an x component and a y component. That's kind of what we're guessing at when we're thinking about the components. But remember, the important thing about a vector is that whether we write a vector in terms of components or in terms of a magnitude and a direction, it's the same vector. They're just different ways of writing out the same vector. And it's very important to be able to go between those different ways of writing vectors interchangeably. So this situation here, thinking about the basis vectors, that's actually not what Newton's third law is telling us about physically what's going on with the vectors. Because however you write the vector, it's still the same vector, just written in a different way. But I can see why you might have gone for it, because they do sound kind of quite technical there. So we're thinking about, well, has it got to be the same or the opposite kind of physical force? And what I mean by this is maybe it's the force of magnetism or the force of gravity or the electromagnetic force. All of those are what we mean by physical forces. And this is a very important thing that I think people don't emphasize enough with Newton's third law of motion, that if we have a force and it has a reaction force, that reaction force, it's always the same kind of physical force. So option A over there. So very well done to the people who got option A, okay, because that's a very important thing about Newton's third law of motion. And if you remember that, that's really going to help you avoid some of the very common misconceptions that we often see when we're thinking about Newton's third law of motion. Okay, so very well done, everybody who gave that question a go. Now, this is a bit of a tricky point. So I thought it might be a good idea to maybe try a couple of examples and see how this works in practice. Let's think about the classic Isaac Newton forces example of an apple and it's falling from a tree and it's falling towards the earth. Let's see how Newton's third law of motion applies in this situation. Now, you probably have noticed by now, whenever we're thinking about a new problem, I'm always saying start by drawing a diagram. Draw yourself a diagram. It's always a great place to start thinking about a new physics problem. So let's start. I've drawn a diagram. Let's see what's going on with the forces. So we've got an apple, we've got the earth. I'll just emphasize it's not to scale, okay? It's not the attack of the giant apple. We don't have a kind of planetary extinction event from a giant apple. I've just drawn the apple nice and big because we're going to be putting some forces on the apple, and it's very helpful to have a bit of space to see what's going on there. Now, we know that there's going to be the force of gravity acting on the apple, and it's a vector, so we can put that on the apple, the force of gravity, and it's a vector pointing towards the earth. So that's all well and good. Let's start by thinking, what's the reaction force to the force of Earth's gravity on the apple? So we've got this question here. We have several different options. See if you guys could find what's the correct reaction force to the force of gravity on the apple. Now, if you're not sure about this one, remember that the reaction force, it's always the same kind of physical force as what we call the action force. So think about what kind of physical force is pulling the apple down. The reaction force has to be the same physical kind of force. Okay, let's see what everybody gets for this one. What's our reaction force? Okay, so nobody's going for option D. We don't like option D. And then some people go A, B, and C. So remember that it's got to be the same physical kind of force. So if we're talking about the force of Earth's gravity on the apple, then the reaction force, it's also got to be the force of gravity. So the correct option here is option C. So very well done, everybody who gave that one a go, especially if you got the reaction force correct. That's really good work. Don't worry if you're not too sure about it. Let me show you what it looks like on the diagram. Let's go back to the diagram that we saw before. So we've got the Earth, we've got the apple, we've got the force of gravity acting on the apple. And as you guys correctly identified, the reaction force to this is the force of the apple's gravity on the Earth. So there we go. That's the reaction force. That's the action-reaction pair. So planet Earth is exerting a force of gravity on the apple, and the apple is exerting an equal and opposite force of gravity on planet Earth. Now here's an interesting question for you guys. If these two forces are equal and opposite, why is it that the apple accelerates much more than the Earth? Now with this question, you don't have to guess. We've covered enough that I know you guys can figure it out. So I'll get this question going. Let's see how you guys do with this one. So if you're not sure about this, one of the other Newton's laws of motion that we've just covered is really going to help you find the answer to this one. So think about what we've just covered with the other Newton's laws. That's going to help you figure out this question. Okay, let's take a look at the responses here. Why does our apple accelerate much more than planet Earth? Let's have a look at the responses. So people mainly going for B and D. So maybe the acceleration's equal and opposite, but just to us it looks like the apple's more, or option B. Now, remember, you don't have to guess with this one because we have actually covered everything we need to figure this one out. So let me direct your attention to Newton's second law of motion over here. So force is equal to mass times acceleration. Okay, now the force is equal and opposite. But remember, the mass of planet Earth, obviously it's much, much more than the mass of an apple. So even though the force is equal and opposite, the acceleration of the apple is much, much more than the acceleration of the Earth. So when the apple's falling towards the Earth does accelerate a tiny, tiny, tiny bit up towards the apple. And the ratio of how much they accelerate, it's the ratio of their masses, okay? So the apple, it's only going to weigh maybe 100 grams, something like that. So the apple accelerates much more. So correct option is option B. So very well done, everybody who got that one. Now, the last question I'd like to try with you guys for today really focuses on one of the misconceptions that we can get when we're thinking about Newton's third law of motion. So we've got our apple, it's falling towards the ground. Let's think about what happens when the apple actually reaches the ground. So eventually the apple's going to reach the ground and it's just going to be stationary on the surface. So let's think, what's going to be the reaction force to the acting on the apple once the apple is on the ground? So I'll get this question going. Let's see what everybody thinks for this one. Now, if you're not sure about this, remember that everything we've learned about Newton's third law still applies. So the reaction force, it's still going to be the same physical type of force. So have a think about this one, take your best guess, and I'll see what everybody gets for this one. Okay, this might have been a bit of a tricky one. So let's see what everybody gets for this one. What's the reaction force? Okay, so people mainly going for A and C. Let's see, what have we got? So A, it's the normal force of the ground on the apple, and C, the force of the apple's gravity on the Earth. Now, I can see why a lot of people might be going for option A. Maybe you've heard of the normal force before. Maybe this is something you might have been covered a bit in school. But this is actually a very, very common misconception when we're thinking about Newton's third law of motion. Remember that the reaction force, it's got to be the same physical kind of force. So if we're thinking, well, what's the reaction force to the force of gravity? It's got to be another force of gravity. So the reaction force, the correct answer, is the force of Earth's gravity, the force of the apple's gravity on the Earth. So option C. So very well done, everybody who got this one. Now this is a bit of a tricky one, and it still might be a bit confusing. So what I'd like to do is just have a couple of slides really focusing on this. Hopefully we can clear up any misconceptions. So we have this situation here. The apple, it's got the force of gravity of the Earth acting on it. But what's changed is that now the apple is on the surface of the Earth. Now, when the apple was falling towards the Earth, most everybody got that the reaction force to the force of Earth's gravity on the apple is the force of the apple's gravity on the Earth. Now, this is the really important point, that just because the apple has reached the ground and has come in contact with the surface, that doesn't change at all. So if that was the action-reaction pair when the apple was falling, it's still the action-reaction pair when the apple is on the ground. So the Earth is still having the force of gravity on the apple, and the apple still has its force of gravity on the Earth. The fact that the apple's reached the ground doesn't change anything. So where does the confusion come from? And people often go for the normal force. Maybe you've heard of the normal force before. Let's think about what's going on there. So what happens when the apple reaches the ground? What we actually get is that as the ground gets compressed, that's what stops the apple from just falling all the way to the center of the Earth. So what we get is that there's a force from the ground. It's called the normal force. It's actually not a great name for a force. So the ground is exerting what we call a normal force on the apple. But remember, Newton's third law of motion still applies. So if the ground is exerting what we call the normal force on the apple is also exerting an equal and opposite force on the ground. So we have two sets of action-reaction pairs. We've got the forces of gravity, and then we've got the normal forces. Now the normal force, you can try it for yourself if you just push down on something, okay? So if you push down on something and the surface is pushing back up on you, that's what we mean by the normal force. And it's pushing back up on me as hard as I'm pushing down on it. That's what we mean by the normal force. Now, why is this such a common misconception? People very often think that the reaction force to the force of gravity, it's the normal force. And you might even read this if you're looking up this online on some websites, or some people even get taught this in school. So why is it such a common misconception? Let me share with you my hypothesis for why this is, because I think it actually helps to understand what's going on with all these forces here. So what we actually have here are two pairs of forces. But I think what happens is it's very easy to forget that we actually live on a planet, and it's easy to think, well, we're just in a lecture theatre or in a physics lab or on a campus, and to just focus on this part of the diagram and to just focus on the force of gravity of the apple, and then we can see that normal force there. Now we're going to find out a bit more next time about exactly why these two forces, they are equal and opposite. But it's easy to jump to the conclusion and think, well, okay, I've got two forces that are equal and opposite right here in this box. So great, that's the action-reaction pair. And it's quite easy to jump to that conclusion and forget about everything going on with planet Earth. And this really relates back to the image that we started with, thinking about Earthrise and really thinking of planet Earth as a planet and not just some kind of firmament where we live and space that's out there, because I think it is easy to forget maybe when you're drawing free body diagrams, when we have workshops and things, it's easy to forget that we are a planet in space, and you kind of end up with just half the picture there. So if we actually kind of return to the picture of Earthrise, I think it really emphasizes this point that, you know, we don't live in a lecture theatre or in a physics lab. We really do live on a fantastic spaceship. And it doesn't just change your perspective on understanding physics and understanding Newton's laws of motion. For me, it really changes my perspective on the planet in an entirety, because this one blue marble here, that's all we have. That's where we all live. I think it's a very important thing to bear in mind, because it really gives you this cosmic perspective on our own planet. So I hope that clears up a few things about Newton's third law of motion. So we've really just kind of covered what they are today. So next time we're going to be looking in a few more details at a few more examples, and this example of terminal velocity, because that's a really great example to really understand everything that's going on there. So just a quick reminder, if you've looked at your schedule on Wednesday morning, we've got labs. Has everybody seen this? We've got labs Wednesday morning. Okay, great. So all you really need to know, there is the lab script there, but just we'll be in labs in New Sciences on Wednesday morning, okay? So we have the drop-in session right now if you have any questions. Otherwise, I'll see you all on Wednesday morning. So excellent work today, everybody, and I'll see you next time.